65,000 tons. That's how much lithium the world produces annually to power everything from phones to electric vehicles. Just 10 pounds of this silvery white metal can move a 4,000-pound car for hundreds of miles without a single drop of fuel. Yet lithium doesn't come from traditional mines. Let's see how 7,000 parts per million of dissolved lithium becomes a battery cell through 18 months of evaporation and precision chemistry. 500 feet underground in the Salar de Atacama. High-capacity pumps extract ancient brine from reservoirs formed over millions of years. This salt water contains only 200–400 parts per million of lithium, barely detectable concentrations mixed with sodium, potassium, and magnesium salts. The brine is pumped to the surface at rates of 50–100 cubic meters per hour and channeled into the first evaporation pond covering 200 hectares. Under desert temperatures exceeding 40 degrees, 140 degrees, water evaporates at 8–12 millimeters per day. The shallow ponds, only 30 centimeters deep but spanning hundreds of hectares, maximize surface exposure to sun and wind. As water disappears, sodium chloride crystallizes first and settles to the bottom. Next, potassium and magnesium compounds precipitate out in sequence. The lithium, being highly soluble, remains dissolved while its concentration increases 20 to 40 times over the original brine. Temperature control determines extraction efficiency. The evaporation rate must stay between 8 to 12 millimeters daily. Any faster and salt crystals form too quickly, trapping lithium. Any slower, and the process becomes economically unviable. Weather stations monitor conditions every hour. If temperature drops below 35 degrees for more than 48 hours, operators add artificial heating systems to maintain evaporation rates. 1 degree variance can reduce lithium recovery by 15%. Brine moves through sequential ponds over 12 to 18 months. First stage, sodium chloride removal at 15,000 to 20,000 BPM salt concentration. Second stage, potassium extraction at $8,000 to $12,000 ppm. Third stage, magnesium precipitation at $5,000 $8,000 ppm. Each transition requires precise timing. Operators measure specific gravity daily, using hydrometers calibrated to 0.01 precision. The ponds change color from pale blue to green to yellow-brown as mineral concentrations shift and salt-loving microorganisms adapt to increasing salinity. By month 15, the final pond contains brine with 6,000 to 7,000 parts per million lithium, a 30-fold concentration increase. This single hectare of concentrated brine holds enough lithium for 1,500 electric vehicle batteries. The Atacama operation processes 1.2 million cubic meters of brine annually, producing 18,000 tons of lithium compounds, enough to power 400,000 electric vehicles. At the processing plant, the concentrated brine enters purification tanks, where calcium hydroxide removes magnesium impurities present at levels 10 to 50 times higher than lithium. The magnesium precipitates as solid particles and settles within 6 to 8 hours. After filtration through 50-micron screens, sodium carbonate is added to trigger lithium crystallization. The lithium transforms from invisible dissolved ions into visible white crystals, settling at 2 to 3 centimeters per hour. Recovery efficiency reaches 85–90% from 7,000 ppm dissolved lithium to 99.5% pure lithium carbonate powder. This crystallization process, perfected over 40 years of industrial development, determines the economic viability of the entire 18-month extraction cycle. Moisture control during crystallization requires atmospheric humidity below 15%. Higher levels cause crystal formation irregularities that reduce purity by 5 to 8%. The reaction temperature must maintain 85 to 90 degrees Celsius with plus 2 degrees Celsius tolerance. Cooling rate during crystal formation cannot exceed 1 degree Celsius per hour, or crystals fracture, creating powder instead of uniform particles. Laboratory analysis checks lithium content every 2 hours using atomic absorption spectroscopy accurate to 0.01%. Each batch processes 50 to 80 tons of brine to produce 1.8 tons of lithium carbonate. From this powder, the transformation to battery begins. The lithium carbonate travels 15,000 kilometers, from Chilean deserts to Asian battery factories. Inside climate-controlled facilities with humidity below 1 ppm, 1,000 times drier than normal air, the lithium mixes with nickel, cobalt, and manganese at 1,400 Wh, 2,050 George, to form cathode crystals. A single gigafactory processes 50,000 tons of lithium annually, enough for 1.2 million electric vehicle batteries. The entire global lithium supply, 400,000 tons of reserves, could theoretically power 300 million electric vehicles, representing a complete transformation of global transportation. Quality control tests every batch for purity, using X-ray diffraction and chemical analysis. Lithium content must exceed 99.2%, or the batch goes to industrial-grade applications at 40% lower price. Approved lithium carbonate is sealed in 25-kilogram moisture-proof bags under nitrogen atmosphere. Each container ship carries $2,000 3,000 tons of lithium compounds worth $45–60 million. The material reaches battery factories where final testing verifies particle size, 10 to 50 microns, surface area, 0.8, 1.2 YURG, and trace metal contamination below 100 ppm. Failed batches, approximately 3 to 5%, are recycled through the purification process. 18 months of evaporation, 7,000 ppm concentration, 1,400 g/Nars crystallization. Modern lithium extraction transforms ancient desert brine into the energy storage that powers electric mobility. Yet 95% of lithium remains unextracted in global reserves, enough to electrify every vehicle on Earth 3 times over. Which critical material extraction would you want to see next? Drop your suggestion in the comments and subscribe for more industrial deep dives.